Okay, so I will draw the device again. Okay, this is my source, this is my gate, and this is my drain. I will be applying a positive voltage between the gate and ground. This is VGS, right? And this source terminal I will ground. And remember, this source terminal was also connected to the body, right? So the body is also grounded. And then grounded to your reference point, ground, like the circuit ground, right? And this I will also connect to ground initially, right? If we do that, and then again we had the N channel here, N channel here, N material here, N material here, and we had the oxide layer here, and then we had the metal layer here, right? So we had the metal layer, the oxide layer, and then the p-type p-type material here with majority holes and the minority electrons. So what did we do? We started applying a gate voltage. This gate voltage, what does it do? With respect to the source, there's a voltage VGS, right? That is a voltage that exists. How about with respect to the drain? There's VDS, fine. Gate to drain, VGD, right? Gate to drain voltage is VGD. So what is the gate to drain voltage in this case? It's equal to VGS, right? I'm trying to see what the voltage is at this point with respect to this point. This point is ground, this point is VGS. So it just happens to be VGS, right? But forget about it just happens to be. Think of Kirchhoff voltage law around the loop. What is the loop that I'm talking about? I'm talking about VGS, VGD, and then the other thing we're going to be interested in is VDS, right? This one here is VDS, right? These are my three terminals: source, gate, drain. I have voltage between these two, a voltage between these two, and a voltage between these two, right? So, and this is a loop. If you think of it, if you think of it this way, it's a loop that's connected through the ground terminals. So I have a voltage with respect to what? With respect to ground, right? So what does this loop mean? This means that VGD is equal to VGS minus VDS, right? Do we agree with that? Yes, sure. Which in this case, because VDS is 0, so if VDS is 0, so VDS equals 0, then VGD will equal VGS, which is what we concluded, which is what we said initially is the case in this point, in this easy, simple case, because it's clear. This is voltage here with respect to ground, voltage here with respect to ground, and they're equal. So this equation is important. Okay? So if that's the case, any voltage differences, they cause electric fields. Any electric field will cause a voltage difference, or any voltage difference will also cause an electric field, right? So now I have between my gate and, again, this is my source. So between the gate and the source, between the gate and the source is also the same potential as the body, right? The source is connected to the body, so it's at the same voltage, right? So this source is at the same potential as the body. This source is also the same potential as the drain. So the voltage difference between the gate and everywhere around the device is the same, right? So the electric field due to this will be sort of the same all over the device, and it's emanating from the gate, right? So what does that do? We have an electric field. Let me draw an electric field this way, emanating from the gate, okay? What does an electric field do to now I have charge carriers that are majority, charge carriers that are P. and then minority charge carriers that are electrons, right? So electrons, they will travel with the electric field, right? So electrons, the holes will travel with the electric field, correct? So the holes, these P devices, will travel with the electric field. So this is all P material, right? This was all P material. So all the P material that I have here has a lot of holes, free holes in the silicon that can carry charge. So I pushed them all down, and I created a depletion layer. So how they draw this? So I drew something here, some depletion layer, a zone here that's free of holes. What else does this the green electric field do? It will have the electrons move against the electric field. So these electrons here, so these holes are all moving with the electric field. Holes moving with the electric field, down, away from the gate. The electrons, they're going to move towards the gate, against the electric field, right? So this is the electric field. The electrons move against the electric field. So they will move against the electric field, and they will all accumulate here. Forming the channel, right? And this was all due to what? The fact that we have VGS and VGD. So we are applying a gate because VGS is equal to VGD, right? So because we applied a voltage at the gate, all of this happened. This voltage has to be greater than a certain threshold for the depletion layer to develop, right? And it also has to go beyond that with a voltage called over voltage for the channel to develop, right? So it has to be beyond VT. VT was what? Between 0.3 and 1 volt, because this is going to be important. Okay, VT it's a device characteristic. This is the thermal voltage, right? It's between 0.3 and 1 volt. I have to be beyond that to create the depletion layer, but I still did not create my channel. I have to go beyond that with a certain amount to start with a certain amount called over voltage.
Can you say that again? VGS has to be greater than VT.
So if VGS is equal to VT, I've created my depletion layer. So this is enough voltage to create depletion layer, depletion zone or layer or whatever you want to call it. So this is VGS equal to VT is enough to create this depletion zone, the depleted of the majority carriers. Now, but it's not enough to create to attract the minority electrons to create the N channel. So for me to create the N channel, I have to have VGS greater than VT. How much greater than VT? It's called the over voltage. So over voltage is what? Is VGS minus VT.
And that
over voltage.
Over voltage is the voltage needed to attract the electrons.
Yes, that's the voltage required to attract the electrons and create the channel. The more over voltage that you put, the more electrons that we will easily be able to attract, and hence you will create this thicker channel, right? Thicker channel, if you look at the cross section, means you have a larger area for the electrons or the electrons here to flow, right? If you create a thicker channel, then you have a larger area, cross section area for the channel for the electrons to flow, right? So this will control the thickness of the channel. The over voltage will control the thickness of the channel, right? In this situation, it controls it on this side and this side. Why? Because VGS is equal to VGD, right? Since VGS is equal to VGD, then I have a voltage, an electric field here that is able to create a certain over voltage in this zone. And that's due to VGS. And VGS now is greater than VT with a certain amount called over voltage. Similarly, on this side, I have VGD. This VGD is what caused the electric field on this side as well, right? So the electric field is due to the voltage difference between the gate and the different areas, right? Between the gate and this area, right, it's due to VGS. Between the gate and this area, the voltage difference is VGD, right? VGD was equal to VGS here, right? So on both sides, I have a voltage that is greater than my thermal voltage VT with a certain amount called the overdrive voltage. So now, what is the thickness of the channel at the beginning, meaning close to the source? And what is the thickness of the channel at the end, meaning close to the drain? It's the same, because it's controlled by the overvoltage, which happens to be the same on both ends now. Okay? We're fine with that? So that's the beginning. Now I start adding voltage here. VDS. And this voltage is less than, for now, it's less than VT. Less than VT. So if it's less than VT, is it greater than or equal to the overdrive voltage? Remember, the overdrive voltage is the voltage beyond VT which the gate is supplying. So now I'm telling you I'm putting a voltage on VDS smaller than VT. So let's say 50 millivolts. Remember, for you to affect the width of the channel, what do you need? Do you need VT or do you need overdrive?
So,
Yeah.
can you back substitute?
And what?
Isn't VOV equal to VGS minus VT?
Sure.
That means VG is equal to VOV plus VT.
Yes, sure.
Then I can back substitute the inequality.
Sure, but think of it from a physical perspective. I think we agreed now that okay, without the source, the thickness of the channel. Our interest is in thickness of the channel. Okay, without the source, the VDS, the thickness of the channel is controlled by the overdrive voltage. The overdrive voltage is a voltage that is beyond VT. So only if the gate voltage here is beyond VT am I going to affect the thickness of the channel, right? Now, with this new situation, okay, let's go back and this is our important equation that I said before, right? This one here, VGD. So VGS is not going to change, right? Does VGS change when I put VDS? No, VGS is VGS. VGS is the voltage between, the source is still grounded. The gate still has a voltage source, VGS applied. So does VGS change? VGS does not change, right? Everybody agrees with that? So the electric field between the gate and the source area here does not change because the voltage difference is the same. Yes?
So I was just thinking, since all the electron or the proton, the positive charges go all the way to the bottom, would that create a difference between the body and VGS in terms of potential?
Body and VGS, of course.
Oh, no,
Because the body is grounded, it's the same
I'm
potential
sorry,
as the source.
To the source terminal, is there going to be
They're
like
connected. They're connected. They're physically, electrically connected. So
Yes,
there's
so
no
there-
potential
there-
difference.
Oh, there's no. Okay.
There's no potential difference. Remember, a p-type material by itself is an insulator. N-type material by itself, so there's no current flowing there. So, and I connect them. So there's no current and I connect them. What does that mean? That means that they're at the same potential. You put two resistors like this and connect them to each other. But you don't have current flowing. Okay, and put a voltage source. You put a voltage source here and put two resistors here. And this is open circuit. Well, what's the voltage at the resistor terminals? The same, right? So it's the same. So there's no current flowing in here. Okay. So I brought these down. They're there. They're in the p-type material. So now we all agree still that even if I put this small VDS or I put big, small VDS, whatever it is, then this VGS will not change. So if VGS does not change, then if this VGS is a little bit greater than VT, then the overdrive voltage in this zone is the same. So the thickness of the channel in this zone will not change. Right? Now let's look at this area. Right? This area, the area around the drain. I've now placed VDS. Go back to our equation for VGD equals VGS minus VDS. So what does VGD equal? VGS minus a small value of voltage less than VT. Right? If it's less than VT, am I creating a VGD that is sorry, if it's less than VT, this is very small, right? So VGD in this case will be approximately equal to VGS, but I have to subtract the VT from it, right? Because assuming VDS is a little less than VT, right? If it's less than VT, it is not creating an overdrive, right? If VDS, remember VGS was only creating the overdrive when it went beyond VT. Now, what is VGD? VGD is VGS minus VDS. VDS is equal to what? Is equal to VT, for example. If it's equal to VT, let's say it's equal to VT. It's a small value. If it's 0, then it's equal to VGS. Then the channel here is not affected, right? If it's equal to VGS. Now it's equal to something a little less than VT, which is very close to 0. If it's close to 0, or if it's less than VT, or if it's a small number, is it going to be very different than VGS? It's not going to be very different than VGS. If it's not very different than VGS, then it has the same overdrive, right? Same overdrive. The overdrive is very similar. Do we agree? If VGS has some overdrive, that is equal to the gate voltage minus VT. Now VGD is equal to VGS minus VDS. So let's say now VGD is equal to VGS minus. Okay, sorry.
Do we want them to be to have the same drive?
Overdrive? In certain, if the VT is small, yes. If VT is small,
How would it affect?
it will affect the characteristic. That's what we will see. But we're going to the whole characteristic now. Initially, current is not flowing. Remember, what's our objective? To calculate the current. That's our objective. When VDS is 0, there's no current flowing, right? Now VDS is small. If VDS is small, then VGD is almost equal to VGS, right? For VDS is small. This does not really affect the equation. So VGD is almost equal to VGS. VGS is equal to the overdrive voltage plus VT, right? So VGS has gone beyond VT enough to create some overdrive, which controlled the thickness of the channel. So now my thickness of the channel here is controlled by proportional to the overdrive voltage. How about now? What's the thickness of the channel here controlled by? Approximately. The overdrive voltage as well, because VGD, because again, remember, the thickness of the channel is due to the electric field in this area, right? So you have an electric field that's going to pull the minority electrons, right? So, and create the channel. This electric field in this zone is created by the voltage difference between the gate and points around this zone. So what is this voltage difference? This voltage difference is VGD. Is VGD very different than VGS if this voltage VDS is very small? It's not, because of this equation. VGD is equal to VGS minus VDS. VDS is very small. It's very small, 50 millivolts. So which means that VGD approximately equals VGS, right? Which means that since VGS has enough overdrive, that means VGD also has similar overdrive voltage to create a similar thickness of the channel. Do we agree with that? Okay? Which means that the channel thickness did not change. But what did I do now? I've added an external voltage, VDS, that is modifying the electric field. That's changing the electric field by a very small amount. I mean, it's not exact. I mean, since I have some voltage, it's not like not having voltage, right? Right? I mean, the VGS and VGD are not exactly the same. There is a voltage difference between them, right? If they're exactly the same, it's only when VDS is equal to 0. Since there is a voltage difference between them, then I have this voltage difference between the drain and the source, right? I've added a small voltage difference between the drain and source. Do we see that? So this equation comes from these three voltages summing up, right? So now I've added a small value for VDS. This small value is not enough to change the thickness of the channel. but it exists. It's a value that is a potential difference between the drain and the source. If I have a potential difference between 2 points, that means I have an electric field between these 2 points. What is that electric field going to do? This electric field now, which is in this direction,
push them.
exactly, it will push the electrons, the free electrons in the channel. So there's an electric field now between D and S, right? D and S, due to this small value that I've added, that is less than VT. This is an electric field that was added here.
So VDS will create an electric field between D and S.
Of course, anytime you have a voltage difference, you have an electric field.
So it's better to take like if the difference is really huge.
And we will increase the difference, and this electric field will increase in value. And let's see what happens. It does more than one thing here, okay? So here, now, because remember, it will do 2 things. It will work on the channel. It will affect the channel. Why? Because we have to apply here. We'll have to look at what VGD is. If VGD is very different than VGS, then the thickness of the channel on this side will change, right? Because the thickness of the channel is controlled by the amount of overdrive that VGS is providing. So amount of voltage above VT that VGS is providing. This is not changing for VGS at all. On this side, on the source side, it's never going to change. So the thickness of the channel will not change on this side, right? On the drain side, the thickness will be changed because VGD will change. As soon as we keep adding more VDS, the thickness of the channel will change. Do we agree?
So the more VDS you have, the thicker the channel.
No. Thicker? Why is it thicker? Look at VG, because the thickness of the channel on this side is proportional to VGD. VGD is equal to VGS minus VDS.
Also,
So the more VDS you add,
the pinching.
exactly, you will start pinching. You will start decreasing the thickness of the channel. Why? Because you're going to start decreasing this voltage VGD, right? VGD is equal to VGS minus VDS. Keep increasing VDS. What happens to VGD? Decreases, which means the overdrive voltage due to VGD is now less, right? Which means that the thickness here will be less, right? I don't want to call it the overdrive voltage due to V. It's the voltage beyond VT that VGD is providing is less. So basically, the thickness here should be written as proportional to VOV minus VDS. Exactly.
So it's
Initially, VDS was 0, so the thickness is proportional to VOV. If I keep increasing VDS, then the thickness will keep decreasing.
just at that side, right?
Just at that side, because on this side, I have VGS. The VGS is not changing. The G is the same, the gate voltage is the same value, and for a fixed value of gate voltage, the source is always connected to ground.
So that's doesn't change.
So there is no change in the thickness of the channel on this side. Thickness on this channel, the channel on this side was originally proportional to VOV only, but now when we looked at this, this plus this plus this is equal to 0, we know that as soon as I increase VDS, I will decrease VGD.
The thickness represents
The thickness of the channel? Thickness of the channel means how many free electrons you have in there. So then you start squeezing. Start squeezing this area.
What happens to electrons when you start pinching it?
When you start pinching it, we'll see. When we start pinching it, remember, when do we start pinching? We start pinching when I increase VDS. Increase VDS means I increase this electric field between the drain and the source.
So it's going to go onto that side?
It's going to increase in value. I don't want to draw a proportion, but it's going to increase in value with respect to what we had before.
thickness decrease, like the amount of electrons is still the same.
The amount of electrons is still the same. Not really. I mean, the area will be less, so the area of the channel will be less, so the amount of electrons in the channel will be less. But something else is happening, okay? Because I increase the electric field. The higher this electric field is, the more it will find some more minority electrons around, and the more it will be able to push these electrons through that pinched channel. Even though it's pinched and it's very difficult for the electrons to pass through, right? What's going to happen is you've increased the value of that electric field. If you increase the value of electric field, you've increased the drift velocity or the drift current, which is due to what? Drift is equal due to the electric field multiplied by the electron mobility, right? So you you lost a little bit because you pinched the channel, so you made it harder for the free electrons to flow from the source to the drain, but the increased electric field also caused what? Did not, after you pinched, the current does not stop, right? Because of what? Because of the electric field. The electric field will see that there are free electrons there in a pinched channel. There's a door that I need to break, right? So this electric field will like break this door and allow the electrons to flow. That's, I don't know if you want to look at it that way.
This electric field will increase VDS.
Increase VDS. Yeah, if you increase VDS, of course, the electric field here will increase. The electric field between the drain and the source. Yeah, drain and the source. Yes. So do we see now what's happening? So I start with a channel, and all of the anytime I add VDS, I will have current flowing. Initially, when VDS was very small, the cross section of the channel was not changing, so free electrons were flowing. Electron flow or charge flow is in a cross-sectional area is current, right? So now I have ID. As soon as I start putting VDS, I start having ID, right? ID is the current that's flowing from the drain to the source. I mean, I don't know how many more things I can put on this drawing.
But we had an equation where
I will get to the equation now. Yeah. So I get to the equation. So this is the current that we're trying to calculate, right? It's coming in from the drain into the source. The same current ID, right? This current is due to the charge, the electrons moving from what? Against the current, against the electric field, right? So electrons are moving against the electric field in the channel this way, creating current in the opposite direction, right? These electrons moving, you can calculate, what is current? Current is rate of change of charge per unit time, right? I is dq by dt, right? So it's the rate of change of charge per unit time in a certain cross-sectional area, actually. Okay, so you have a cross-sectional area where the charges are moving. You stand there with a screen and you keep counting how many electrons are moving, and that's current. That's charge per unit time is current. You stand in a certain cross-sectional area and see how many electrons are moving forward, right? When the VDS is very small, this area, it does not change, right? This area that the electrons are crossing will not change. How about when the channel is pinched? When the channel becomes, pinched on this side, so 0 here and, some value here.
So will electrons move?
You have a smaller area. You have a smaller area for the electrons. You're looking at a smaller area, right? You're looking at a smaller area here, average, for example. The whole area, for example, the whole area of this, you lost this area, right? You lost this area, and you lost it also with the width, right? So you lost the whole cross-sectional area. But the whole area that is allowed for your electrons to move has decreased.
What happens to that lost area? To those
Well,
measurements?
it's a depletion layer.
Okay.
It's a depletion layer finish. You've pinched it. It's a depletion layer.
So like will the electrons will move more together?
They will move. They will find it more difficult to move, right? They find it more difficult to move through that, and then the difficulty was due to what? To a change in area, right? Area is length times width, right? It's 2 dimensions, right? So it's not a linear relationship. It's a squared. Like it's a meter squared or centimeters squared. So you will see that we will see that the current will initially when VDS was small and we did not pinch anything or did not change the area at all, that there was some resistance RD to the flow of current VD, right? And that this relationship between VD and ID, which was the relationship between VDS and ID, was this RD variable. Initially it was linear because the area was fixed, right? And then we will find that if I start varying the area, then the relationship between ID and RD will vary according to a quadratic, because the area is has a quadratic term, right? So we will see that it's going to vary according to a quadratic, right? At some point, so this is no longer going to be RD, a linear relationship. It's going to be a quadratic relationship. And then, when does the channel become completely pinched? When what happens?
It's small
VDS
one.
Again, we look at the proportion. The width of the channel is proportional to over voltage minus VDS. When VDS is equal to the overdrive voltage, the channel on the drain side becomes completely pinched. Right? Remember here the channel width is proportional to the overdrive voltage minus VDS. If VDS is equal to the overdrive voltage, then the channel here is 0. It's pinched. Right?
So VDS equal to V overdrive minus.
No. It's the proportion. The width of the channel on this side is proportional to the overdrive voltage minus VDS. VDS was originally 0, right? So the width of the channel was equal to the overdrive voltage. That's the case without applying VDS. Now I started to apply a VDS. I want some current to flow. I made a device for current to flow, right? So I start applying VDS. For small values of VDS, the channel width here is VOV minus VDS. VDS is small, so the channel width is approximately VOV. Approximately VOV. So it's the same width as on the source side. That's why the cross-section area did not change. So the relationship between the current and the voltage was linear initially in the characteristic. And we will look at the characteristic now. Then we start increasing VDS. We start increasing the value of VDS that I have. If you start increasing VDF, so it's no longer less than VT, you increase it beyond VT. Okay, so VDS starts increasing beyond VT. If it starts increasing beyond VT, then it's different than VGS. It's quite different. Initially, because it was small, it was very similar to VGS. And since VGS was providing overdrive, then I have a thickness here. That's the same thickness here. Now VDS is big. So VGD, which is really controlling the electric field in this around the drain side, is now different than VGS because I'm subtracting a larger value from it. It's different. So the thickness of the channel will be different. Thickness of the channel will be different means the area that the charges are able to go through is different. So the relationship between the voltage ID and current ID that's flowing due to the electric field between D and S, because there's a voltage difference between them, is going to be different. It's not going to be a linear relationship controlled by what we call RD. It will be governed by a quadratic. Okay? And then, at some point, you keep increasing VDS until it equals VOV. Until it equals the overdrive voltage provided by the gate. What happens there? The thickness of the channel around the drain is proportional to the overdrive voltage minus VDS. VDS is now equal to the overdrive voltage. So the thickness of the channel is 0. Right? So I made the thickness of the channel 0. So at this point, I'm still governed by the quadratic. I'm still governed by the quadratic because now my area is still changed to, this is the last time the area will change. Right? This is the last time that the area that the electrons flowing through will change. Because I'm pinched, خلاص, I'm 0. So this is the smallest area that the electrons will be able to go through. So this will be the end of the quadratic relationship between the voltage and the current. Okay? After that, what's happening? After that, what's happening? VDS is greater than the overdrive voltage. Can I pinch anymore? I don't have pinching. I pinch it to 0. So if I pinched it to 0, now I'll erase all of this now, okay? If I pinched it to 0, now let me draw, so this is my thickness of my channel. I've pinched it to 0. This is my source, and this is my drain. And this is the end of so this is the relationship between VDS and ID. And we will look at the equations next, but as long as we all agree now that originally when VDS is smaller than the VT, then the relationship between them is linear. Then what happens? Then it's quadratic because the current and voltage are related by this change in area. Until when? Until VDS is equal to VOV, which is called VDS saturation.
Then you will combine it.
Yeah, because you saw this in the textbook of why. The area is not changing, so I agree. The area is not changing, so sure, I agree. The area is not changing So the relationship between ID and VD is no longer governed by this quadratic anymore. The area is not changing. There's no change in area at all. So you increase VDS, area is not changing. Area of the channel is not changing. Khalas, you've pinched it. But what happens to the channel? You know, it was pinched because, why was it pinched? Because when VDS was equal to VOV. Now let's look at the voltage profile across the channel, okay? Because this is where a lot of people got confused before. So now let's look at the voltage profile across the channel. This is the voltage profile across the channel. I will draw it on this axis, okay? So this is the drain, this is the source, okay? And this is voltage drop across the channel. What is the voltage at the source? At the source, voltage at the source. Come on, 0. The voltage at the source. My source is grounded, right? The source is grounded. So the voltage at the source is 0. How about the voltage at the drain? VDS. We agree? So it's some VDS value here. Okay? So between them, there's a, fine. There's a voltage drop, you know. I mean, the voltage drop was 0 here, and then VDS here. So between them, there is a different voltage drop, right? In this case, when the channel is pinched at the drain, what is VDS equal to? VOV. Very nice. Okay. Now let me start increasing VDS beyond VOV and see what happens. I will draw the same situation. So I will draw the voltage drop. First I drew the channel width. This is the channel width, right? Now I will start by drawing the voltage drop first, and then I'll draw the channel width, right? So I will draw the voltage drop across the channel first, and then we'll draw the channel width, okay? So the voltage drop across at the source, does anything change? The voltage is still 0 at the source. How about at the drain? What's the voltage? What is it? It's equal to, still V equal to VDS. It's equal to VDS, but it's greater than VOV. It's equal to VDS. Still VDS, right? I mean, you have, again, source connected to ground, drain connected to VDS. So it's always going to be equal to VDS, right? This is VDS, right? So it's always equal to VDS. Just VDS here happens to be greater than the overdrive voltage. The overdrive voltage is what makes the channel pinched at the location where the voltage is equal to the overdrive voltage, right? So the channel was pinched at here. Why? Because the voltage across the channel was equal to VOV. It was created by VDS, but it's equal to VOV. Now let's see what's happening. Still, my voltage at the source is 0. Voltage at the drain is VDS. But VDS is greater than VOV. So VOV is where then? Somewhere, this is voltage, right? Magnitude. This is voltage drop magnitude. VOV is where? VOV is here, for example. It's less than VDS, right? We said VDS is greater than VOV. So VOV is somewhere here. The value of the overdrive voltage is somewhere here. So if I increase VDS beyond VOV, it means that the voltage at the drain is VDS, which is greater than VOV. Where is the voltage VOV? Where is the voltage drop across the channel? That is equal to VOV. It's a little bit before. It's between the source and the drain. So what does this mean? Now I want to draw the channel thickness. Here, does the channel thickness at the source change? No, because it's still proportional to VOV. Because VGS did not change. What increases? No. Remember, what did we say here? The channel thickness becomes 0 when the voltage across the channel becomes VOV. Okay? So where is the voltage across the channel equal to VOV? Here. Not at the end. So I would become pinched here. Okay? So I become pinched here. And then this is all pinched. Right? I've pinched my channel. I no longer have a channel thickness. Right? But even though I pinched my channel, I don't have a channel thickness, so I made it very hard for the current to flow. Right? So increasing voltage made it very hard for current to flow. It's like adding a large impedance to current to flow. Right? That's why the characteristic after that becomes like this. Right? That's why the characteristic like after that becomes like this, straight. So beyond VDS, when VDS is greater than VOV, the characteristic becomes like this. So current will still flow. It's so hard for the current to flow, right? Because this is the value of current that was flowing. It's not like if I increase just a little bit the voltage, doesn't mean the current will stop flowing. It will flow, but you will not have higher current flowing. It's like starting to, if you keep increasing the voltage and I keep increasing the impedance. Keep increasing the voltage and I keep increasing the impedance. It's like a larger and larger impedance to the current flow, right? So that's why the characteristic becomes like this. So, and this becomes really nice. And this is all at what? This is all at a specific VGS. Do you agree? All of this I was fixing VGS because the overdrive voltage was fixed. Now let's say I change VGS, what happens? If I change VGS, I change VGS and I now sweep the characteristic again, I get something similar. Sorry. Right? I change VGS again, means I change my overdrive voltage, means I do the same, right? This whole process again, I will get similar, different characteristics here.
No, but after like the compression and stuff, so like there would be no electrons to flow or what? Like
No. The electrons are the free electrons are still there in the channel. You still have channel thickness. You pinched, but what did you do? You still have an electric field due to VDS. The VDS electric field will see these electrons. Now you're a stronger electric field. It will see the electrons in the channel that was pinched further away, and will pull them through. Right? It will pull them through, but it will be hard. That's why it's a higher impedance to the current flow. That's why the slope. What is the slope of this? Slope is delta I over delta V in this case. Right? So remember, V equals I times R. Right? So I over V is equal to 1 over R. So the slope here is equal to 1 over R. Slope here is what? 0, which means R is infinity. Right? So does it make sense? So this is the whole characteristic now. I hope makes sense. Okay, that's good. So now we can just use fill the equations. And now it's a matter of equations. So here we will have a quadratic, initially linear, but linear. And it's a very small zone, right, for VDS. So the quadratic actually, we found that the quadratic will actually satisfy this whole operation until this point, saturation point. And remember, the saturation point is different for every value of VGS because the overdrive voltage is different. So you will find that the saturation point will change this way.
so the impedance is infinite.
Here, theoretically speaking, yes.
Is it a good thing? Why is it a good thing?
Why is it a good thing? Remember our amplifier stuff? We wanted stuff to look like, we wanted input impedance to be infinite. We want output impedance to be 0 for what? If the output impedance, if we use the model for the voltage source, dependent voltage source in the output, right? If this was a dependent voltage source. How about if I wanted R here to be 0? How about if I use the model for the dependent current source? If I use the model for the dependent current source, I wanted the output impedance to be what? Exactly. This is the output impedance for the dependent current source model. I wanted this output impedance to be infinite. So what we will find from the equations is that the device in this region, which is called the saturation region, this is called the saturation region. We will find that the value of the current here, the value of the current here. So this is current that is fixed, right? It's current that is fixed. That depends on what? This is one value, depends on this gate voltage. This is one value of current, depends on this gate voltage. This is one value of current, depending on another gate voltage. Does it depend on anything besides the overdrive or the gate voltage? No. So we have a voltage-controlled current source. Right? It's a current source. It's a fixed value of current. Means I have a current source. How am I controlling this? I'm controlling this by specific overdrive, overdrive 1, overdrive 2, overdrive 3. So I have a voltage controlled current source.
You can make a regulator by
So I have a
current.
current, exactly. So I have a current source and an infinite output impedance model, which is great. That is wonderful. I can control with depending on my input. Now this is my output stuff. My input is what? Yeah, input was what? My gate voltage. VGS. Right? So I have input that is voltage, infinite input impedance. Right? I'm not drawing any current. Am I drawing any current at the gate? It's a capacitor. I'm not drawing any current. So I'm just adding voltage. So I have an infinite input impedance because I am not drawing any current at the input, and I'm not losing any voltage when my load changes because I have an infinite output impedance in parallel to the current source.
That's why like the impedance is infinite, because we don't want any current, we just want ID yani, to be the one who affects the stuff.
I want ID to be controlled by the gate voltage, right? Which means that I want this current here, I want this current that's going to flow out of my device to be controlled by my input parameter. I want this current to be controlled by my input parameter. That's nice. Then I can put a small voltage and control a huge value of current, right? So that's the beauty of the model.
Current will not be
I put a gate voltage, VGS. Remember, VGS is by control input now, right? That's my. All of this happened at different. This curve we said is at one gate voltage, meaning one overdrive. This one happened at another gate voltage, another overdrive. This one happened at another gate voltage, another overdrive, right? So my gate voltage, if I operate only here, that's maybe you're confused because of that. If I now find a way, remember my DC operating point for the diode? What did we do? We biased the diode to operate in a certain position. And then we looked at its voltage regulation, small signal analysis. So now what I will do is bias the transistor to operate in the saturation zone. If I operate in the saturation zone, my model, remember for the small signal, after we biased it, we came up with a model. Now, when I bias the diode, I will come up with a model for the DC operating point. This DC operating point is going to be a certain value of current, ID1, at a certain value of voltage, VDS1. Right? You will have to create these conditions. Why do you want to operate in the saturation zone? Because in the saturation zone, you have a value of current that is not controlled by the voltage across the device. It's actually controlled by your control signal, the gate voltage, which is nice. Right? The gate voltage, you're not drawing any current. I have something that is not, I'm not taking current from it. So it's like if you have a sensor. You put your sensor there, for example, you're not going to draw current from the sensor. But I will just measure the voltage across the sensor. I will trickle current. Right? The capacitor, what it does is charges using that current, and that's it. It maintains the voltage. So I will put my sensor across that input capacitor, for example. It will charge the capacitor a certain voltage, and that's it. This is my temperature, for example. I have a certain gate voltage. This gate voltage will mean that I'm following one of these characteristics. Right? If I'm following one of these characteristics, I know that as soon as now I put VDS greater than the overdrive voltage, I'm operating, I have certain current through my device. Right? Remember, I put a first certain gate voltage. This gate voltage is controlling which characteristic I'm on. Let's say I'm now on this characteristic. Now what? Now I put a certain value of drain voltage. That's greater than the overdrive voltage. How much greater? Does it matter? Does not matter. According to this, does not matter. I put some, as long as it's greater than the overdrive voltage, I get my current. Remember that my output, my model will look like a voltage-controlled current source. So I'm going to get a fixed value of current. So I'm amplifying the current. I'm amplifying the current regardless of the voltage across the device. That's a nice characteristic. Right? So if I change the gate voltage, I can change my current. Change the gate voltage, I can change my current. Even though I kept the same value of VDS. Right? So for the same value of VDS, changing the gate voltage will make you operate here, or here, or here. Right? Which means you can have a certain current, this one, or this one, or this one. So I can, at the output now, I can push current into my output that I control. It's controlled by me. By what? By the gate. So it's a voltage input, current output. Remember that models for chapter 1? We had ones that are voltage input, voltage output. Voltage input, current output. Current input, current output. So this is a voltage input, current output type model with an infinite output impedance in parallel with the current source, which means it does not affect the operation, the value of the current. This is all ideal, okay? We will have a section in the text that I will skim through as well, where, okay, fine, this is nice and ideal. Our output is infinite. Fine, nice. Why is if it's infinite, it gives me the straight line. We agree? But is it really infinite? Is there such a thing as infinite? There's no such thing as infinite, because if I keep increasing VDS, then this electric field that is between the drain and the source is doing what? It's going to find any minority carriers that are floating around and make them drift as well. So it will add a little bit of current, right? So in the real case, this curve is not flat. It's has some slope, right? It has some slope because fine, you're increasing VDS, increasing this electric field. You increase the electric field, any minority carriers will be drawn to this electric field, and they will cause some current to flow. So there will be some current flow. So this resistance will not be infinite. It will be some value, finite value of resistance. This will be big, because the slope here is definitely big compared to the slope here, right? So I mean different compared to the slope here. So it's it's still a big value, but it's a good approximation to think of it as just a flat. Okay, so that's all the physics behind the ton of equations I'm going to give you now. Okay, but all of these equations are what? Are equations for ID. They're all different equations for ID.
That depend on certain values.
One, exactly. They will depend on certain values of gate voltage that I'm applying. One will be linear. One will be a quadratic. And one will be an equation that will not depend on it will be depending on the quadratic, but it will not change with VDS. You will have a VOV, you will remove the dependence on VDS and replace that with the overdrive voltage. Okay? Okay, so everybody's cool with this? Alhamdulillah? So you didn't miss anything yesterday? Okay. So now let's skim through all of these equations quickly. Okay? So now. So this is the first equation. Yeah. So this is the first equation. This is the case where what? The relationship between VDS and ID is governed by a linear relationship, right? That is controlled by the gate voltage. So this is the initial stage. Canvas, desktop, background. So this is this initial stage. These are the same equations. They just replace the overdrive voltage with VGS minus VT, right? So what is this? This is the conductance, the 1 over the resistance, right? And what is it? Where is it coming from? It's coming from, okay, calculation of how much charge is moving. How much charge is moving will depend on the mobility of the charge, will depend on the size of the capacitance, that you've created, because you have a certain plate that has a certain dimension, certain area, size of the capacitance, and then the form factor of the device, the width of the device, W.
What is that equation working?
This is current. This is all the equations we're going to look at are current, drain current, the current that's flowing from my.
For the linear.
Yeah, this is the linear region where this equation is for VDS is less than VT. VDS less than VT region, right? The relationship between ID and VD will be governed by some parameters that are mostly, this is the width of the device, length of the channel, size of the capacitance, mobility of the holes, okay? Overdrive voltage. So the value of the overdrive voltage will dictate the value of the term that is connecting ID and VD.
So,
right?
Mu n C AX, this is the.
Mu n is the mobility of the electrons. How easy they can pass through the channel.
This is the
COX, yeah, all of this is the conductance. Yes, it's
All
the
of it.
yeah, here. So this is the conductance. This term here in brackets is the conductance of the device, which is 1 over the resistance, right? So this conductance, does it depend on anything that is nonlinear? No, these are all constants. It's a constant, it's a constant, it's a constant. And this is your over voltage controlled by your gate to source voltage. This is controlled by your VGS. This overdrive is controlled by the VGS. Right? So remember, at every value of VGS, I will have a different slope for that characteristic. That's what we talked about.
So this is equation 1.
This is the first one. Okay, we're happy with this? Okay. Now let's go to the next one. Next one happens when what? Now I keep increasing VDS. So this is, the drawing that we just drew by hand. Now VDS is increased. VDS increases beyond VT. Right? So if VDS increases beyond VT, we're going to go into this quadratic mode. Right? So this is the VDS increasing, current is flowing, and because the thickness of the channel is controlled by VDS over voltage minus VDS, right? Thickness of the channel is controlled over voltage minus VDS. So since VDS increased, the thickness of the channel here decreased, right? So now, and the decrease was proportional to this change in area, right? So this change in area means I have an effective, if I want to simplify my calculations, I sort of will look at the, I will think of this, okay, what is the equivalent rectangular area? This is not a rectangle anymore, so it's difficult to calculate the area for this, right? But what is the equivalent area for the rectangle? It will have a certain thickness. This was my original rectangle. Now I lost thickness, so I look like this, right? But this area here is equivalent to maybe having a rectangle that is like this, right? Right, this area is equivalent to having this area, right? Because this is easy for me. The rectangular areas are easy for me because width and length of the channel, I can calculate the area that the electrons are flowing through, right? So because of this approximation, or the approximation that we wanted to use, we will, instead of the previous equation for current, we had only VOV. Right? We only had VOV in the previous equation for current. If you go back to the previous equation for current, this was my previous equation for current. It had these device-dependent parameters and then VOV. Right? Now, this controlled my thickness of the channel. Now, what's controlling my thickness of the channel? It's VOV and something related to VDS. Right? This something related to VDS changed the thickness of my channel. So what is the average thickness of the channel due to now? Right? It will be due to half VDS. Where does this come from? It comes from the fact that the voltage midway, if the voltage here is VDS, the voltage here is 0, the voltage midway is half VDS. So we said that the equivalent channel depth is due to VOV minus half VDS. So instead of VOV in the previous equation, I replace it with VOV minus half VDS. And then look at this. If VDS is small with respect to VOV, then half VDS is even smaller. So I can ignore this part, and this equation will reduce to the same as the one before. Why is it half? Is again because again the channel width depends on the value of VDS voltage, right? I don't want to do this triangular calculation business, right? So we want to, it means that there's an effective voltage, overdrive voltage across my whole channel now, right? Remember, the thickness of the channel on the source is controlled by the overdrive voltage. On the other side is controlled by overdrive voltage minus VDS. So to make it easier for the calculation, I'm going to think of an effective overdrive voltage that created the thickness of the channel. What is that effective? It's between 0 and VDS. What is it? Half VDS. On one side it was VOV, other side is VOV minus VDS, right? What is it in the middle? VOV minus half VDS. It's like a new thickness of the channel created by half the voltage. That's this equation. Bring VDS inside, and you will see this quadratic, right?
This is where VDS equal to...
That's that quadratic.
Yeah, when VDS equal to...
Greater than VT. VDS is greater than VT. This is VDS, but
the
less than over voltage. VDS greater than VT, but still less than the overdrive voltage.
So it's almost the same as
No, less than VT. No. 50 overdrive voltage is 0.3 to 1. Sorry, VT. VT is 0.3 to 1 volt. Period. We will see that gate voltages are larger than that. Typical gate voltage will use a larger than that. So, but this is still for this is for VDS greater than VT. So this is the quadratic region, right? This will apply all the way until what? Until my area keeps changing. When does my area stop changing? When VGD is equal to VOV. Right? So that's when that area stops changing. The equation is next. So the equation is the equation is next here. So this is the quadratic, right? In this quadratic, what we will do now, this is VDS greater than or equal to VOV. So in the first equation, remember what did we do here? We took my first equation, and instead of VOV, I put VOV minus half VDS. How about the next step? I will remove VOV, and I will keep VOV, but I will remove VDS and replace it with VOV, right? Because my VDS voltage is now VOV, and I will keep my VOV in the original. So it's Kn W over L, VOV times VOV, so it's VOV squared.
So VDS equals to VOV for that equation?
No, for the case where the voltage is less than VOV, I will do what? I will calculate the equivalent voltage creating a channel depth. That's equal to VOV minus half VDS. So in my first equation before, I had VOV here. I had VOV here. I removed VOV and I put VOV minus half VDS. Next, if I keep increasing VOV, if you keep increasing VDS, I will, originally here, remember, I had VOV. I replaced it with VOV minus half VDS for the case where the voltage is still less than the overdrive voltage. For the case where the voltage is equal to the overdrive voltage, so the area is no longer going to change after that, what is VDS? VDS is equal to VOV. Right, so that's what we have next. So VDS equal to VOV is this case.
VDS
So,
equals to VOV.
and that's the end of the quadratic. This point is the end of the quadratic, because the quadratic was coming from the change in area. The area will no longer change. I've pinched the channel, and that's it, I'm done. So this is my VD saturation is equal to VOV. So I've reached the end of the pinching process, if you want, for the channel here. So that gives me that current. And we know that VOV is equal to what? VOV is the overdrive voltage. It's equal to the gate voltage beyond VT. Because typically you will be applying a gate voltage, and you have a specific device that has a certain VT, right? So this is the typical equation you will use. All the way from the 0, VDS equal to 0, all the way until saturation. That's the equation we'll use. After saturation, what will you use? This. Right? Only. It will not change. Because so, yeah, we'll stop here. So this covers the whole characteristic, okay? So next we will look at the P-type MOSFET. We will skim through the P-type MOSFET very quickly because it's very similar to the N-type MOSFET. And then we will look at, this is some theory, I will go through it quickly. And then we will start looking at the DC operating characteristics. So I think one lecture will be DC operating characteristics, which is tomorrow. And then one lecture will be the AC operating characteristics, so small signal. So tomorrow, DC operating characteristics. Yeah, so we will not be able to finish the full chapter, but the rest of the chapter. So in the AC operating characteristics, so we came up with a model, right? We came up with a model for the voltage controlled current source model for the amplifier. That's in the large signal, not small signal. That's the large signal model. We will come up with a small signal model. There are 3-4 small signal models, but they're all the same. They have the same purpose. They are to perform small signal analysis on the device. So we will cover one of the small signal models. Right? Remember the different models that we had initially at the beginning of the chapter? And chapter 1, we had input voltage, output current, input current. We had 4 different models. We typically, we utilized a lot. We utilized one considerably more than the others in the op-amp chapter, right? Here, the MOSFET has, 4 or 5 different small signal models. Okay, we will concentrate on one, and then the rest, it's a different model to do the same thing but it's more convenient for a certain application. Yeah, I mean it's otherwise otherwise we'll have to extend quite a bit class. So we'll cover the main concept here. So of operation as an amplifier for the device, for the MOSFET and the BJT.